This is Lecture 8C on calculating the total mass. We're going to start with looking at the total mass. In fact, understanding the units involved in finding the total mass is really the key to being able to compute the center of mass. Okay, we begin here with the discrete mass, and that would just be a bunch of, say, bricks or objects lying around in some kind of system. Okay, so if the system consisted of a bunch of these masses, to find the total mass, you simply add them up. So if the system had two 4-kilogram masses, three 10-kilogram mass, and one 15-kilogram mass, the total mass in the system is just the sum, 53 kilograms. Most problems, though, especially the ones that require calculus, are specified in terms of density. So in general, density, being a material property, has units of mass per unit volume. And we're going to use kilograms per meter cubed here, not worry about the British units at all. So, for example, your density of copper is, say, 8,960 kilograms per cubic meter. You want to find the mass of an object made of this copper. The total mass is the density, this 8960, times the volume of the material. For one-dimensional problems, the density is specified as a linear density. The units of linear density are kilograms per meter. And I'll show you now how this is achieved. If you get these kind of densities straightened out, then the calculations get a whole lot easier. Okay, so the basic equation still holds. Mass equals density times volume. But let's say we have a wire. Okay, I'm going to draw a picture of it here. So here's your wire. It's got a circular cross-section, which let's say is uniform, even though I haven't drawn it very uniform. Well, let me get rid of that. Okay, so here's my wire here, and it just extends out here with a nice uniform cross-section. So the cross-sectional area of this wire is A, and I have a certain length of it, and I'll call that length L. What is the volume of this piece of wire? It is that cross-sectional area times the length. So the mass is the density, that would be in kilograms per cubic meter. Let me write that in. I'm talking here about the density in kilograms per cubic meter times the volume, and the volume is area times length. Okay, if this area is constant, so you have constant cross-sectional area and a constant density, you could multiply those two together. You could multiply the density times the area together and get what is called the linear density. So the linear density is this material density in kilograms per meter cubed times the area. So if I write that out, the dimensions, I have kilograms per cubic meter, that's the dimensions of the density. I multiply it by area, which is meters squared, and I get kilograms per meter, and that's what I'm talking about up here. The linear density, when I put the little L there, is in kilograms per meter. Sometimes that little L is missing and only the units are written, so be careful on that. Okay, at least I try not to do it, but sometimes it happens in different books. If we're given the linear density, then to find the mass, all we have to do is multiply by the missing dimension, which is the length. So if we had a certain aluminum wire that's gold-plated, say that the linear density is 0.033 kilograms per meter, and I have 10 meters of this wire, I multiply those two numbers together, and I get the mass of, well, it's of aluminum with gold on it, gold-plated aluminum, that I have in this piece of wire that I have in my hands. The idea here is that the manufacturer already multiplied the density of the material by the cross-sectional area of the wire and reported that as a linear density. Sometimes other methods are used to determine linear density. Okay, so now you understand linear density. It is used in one-dimensional problems. All right, now we're going to look at another density, which is the density per unit area. This is going to have units of kilograms per meter squared. We're going back to the same idea here, but let's, instead of a wire, let's say we have some kind of a, get the pretend we've got some kind of a plate. Hate drawing it in that direction, but I will. Okay. So we have some kind of a box here. And the density is specified as kilograms per square meter. So the linear part of the density has been worked out already. It's already been multiplied by the length, and all you have to multiply by is the area you might have cut off. Now if you multiply this density by the area of that little section, length here is constant, then you get mass, which is kilograms. Looking back at the calculation, we have the same as we had before. Mass is density times volume, but the volume is area times length. If I here and I multiply that density times the length, then the area is all that's missing from the mass calculation. So we have this density per unit area is just the material density times the length. If I want to calculate the total mass, I have to multiply by the missing dimension, which is the area. Okay. So if I had a 100 square meter flat plate and it had a density in terms of area of 15,000 kilograms per square meter, then the total mass would be the 15,000 kilograms per square meter times the 100 square meters, which just gives you kilograms. Again, writing that out a little bit just so you see it. So we have mass is what we want. It's in kilograms. And this is going to be a density in kilograms per square meter times the area, which is in square meters, leaving me with kilograms. This might seem rather, I don't know, unnecessary to go through these definitions, but I think these definitions are not stated very well in the text and they lead to confusion. Now we have to look at non-uniform densities, and this is what leads us into the calculus problems. Let's say you have the linear density of material specified, and it's, again, kilograms per meter. Okay. But instead of being constant along the wire, say something happens along this wire. Again, we were talking about some kind of a wire here. Let's say, as you go in the X direction, perhaps the cross-sectional area changes, or perhaps more gold is plated on and makes it the density different. We were talking before about aluminum wire that was gold plated. Okay, so that as you move in X, this density changes. That's why we have a linear density. Its units are still kilogram per meter, but it changes as you move along the length of the wire. What is the total mass? How would you find it? You would do the usual thing you do in calculus over and over again. You would divide it into little sections. In each little section, you would assume that the density was constant, and you'd multiply by the length of the section, which would be delta x. And you proceed here, sum over all these little sections, take the limit as the number of little sections goes to infinity, and you would end up with a definite integral. And here is the definite integral. I'm integrating from 0 to L of rho L, that would be rho L of x, which is my non-uniform density, times dx. The delta x becomes a dx, and I integrate from 0 to, say, L. Okay? And that will give me the mass in that wire. You can see that if rho L of x was constant, this would just reduce to the expression we had before. So let's say along that wire, the non-uniform linear density is 0.033 plus 0.05x, and I should have put the units here. I'll do it now. So this is kilograms per meter. Okay. Then if you have 10 meters of wire, you integrate from 0 to 10 of this non-linear density. This is your rho L of x. Here's your dx. And that will give you the total mass in that wire. Remember before, the mass was rho L times the length of wire. Now we have an integral because the density is non-uniform. The density varies in x. What happens if that other density, the density in terms of kilograms per square meter, is non-uniform? Well, I'm going to write my flat plate like this on a coordinate system, and I'll say, just to make things easy, that the flat plate looks like that. So the upper edge is some function of x. Now I need to integrate over all these areas. Well, what is the area? If I divided this up into the usual little strips, which I'm going to do later to calculate the center of mass in 2 dimensions, then the area will be the area, each little area is going to be the function somewhere in here, let me put the in here, times delta x. And then the total area would be the sum of all these. Of course, I'd have to multiply. If the density is non-uniform, then the mass would be the non-uniform density in this little, say this is xn, okay, and xn, some value there, times the area, which would be this function, times delta x. This is the mass in the nth section. Then the total mass would be the sum over all these sections. I take the limit as n goes to infinity, and you're saying, how many times do we have to do the same thing? And I guess it's as many times as we need to. So using the same procedure that we did before, we end up with a definite integral, and we would integrate from 0, in this case, to L. All right, f of x is the upper edge. By multiplying by f of x dx, we end up with the area. Here is our density. So again, we have kilograms per meter squared. We need to multiply by area in order to get mass.